Hi, it's Mr. Beck. I'm here to tell you today about thin film interference. It's going to seem like a complicated process, but we're going to make it easy at the end, so stick with me. Now, thin film interference, you may have noticed, but you may not have known what you're looking for. If you ever see a soap bubble, you'll notice that there are these wonderful colors that show up, these magentas and greens and such in the surface of that soap bubble. Or if you see oil on the water or after it rains in a parking lot, you'll often see these interesting colors, like not quite a rainbow, but some magentas in there, some greens, some sort of rainbow colors, but definitely some interesting colors there, as well as there's something. This is called Newton's rings. It's when you have this dome of a material or a wedge of material, and you have a little bit of air underneath. You get these interesting rings that are showing of dark light happening. So all of this is the process is based upon the process of thin film interference. So let's take a look at what's going on. With thin film interference, what we have is we'll have a first substance, substance one, it'll often be the air. Next, we will have a second substance, which is the thin film that we're interested in. And then we're going to have a third substance on top of which that thin film sits. So in the case of the air bubble, the soap bubble, substance one would be the air, substance two would be the thickness of the soap bubble itself, and three would be the air inside the soap bubble. With the second situation, with the oil on the water, we could have air on the top, and then oil is your second level, and then water is your substance three. So we're going to have three substances. In the case of the Newton's rings, then N1 is air, N2 is the glass itself, and then N3 is another layer of air. So each one of these will be a situation where we have a thin film in between two other substances. Now, we are rarely going to care what happens after N3. So if there is an N4, just ignore it. Don't worry about what's going on afterwards. Now what happens is we have an incoming ray of light. That ray of light has a certain wavelength, and it's going to come down and hit the surface between N1 and N2. Some of that light is going to be transmitted, and some of that light is going to be reflected. So at every time you have a change in medium, some of the light will be transmitted and some of the light will be reflected. Now, we also have where the light is hitting from N2 to N3, and the same thing's going to happen here. Some is going to be transmitted and some is going to be reflected. And then that reflected wave that comes back up, some of that actually will be transmitted and reflected, but we're really only interested in the transmitted part. So even though some is reflected on that surface, we're going to not worry about that because we're not going to do the calculations there. So what we're really interested in with all of that complicated reflections and transmissions of the light, what we're interested in is what happens to those two waves right there. Now, just as a point of reference, if it's, say, light hitting glass from the air, probably about 95%, 98% of the light is actually going to go in through from N1 into N2 into the glass, and only about 5% will reflect. But on that second surface, the same thing's going to happen. About 95% will go through and maybe 5% will reflect there. And then so what we have is this beam will be about 95% of the original. And the next one will be, oh, I'm sorry, take that back. This beam will be about 5% of the original. And then the other one will be 5% of 95. So almost 5% again. So these are going to be roughly equal in intensity when we get down to it. So that's what's going to be interesting. And then those two waves, when they come out, what's going to happen is if those waves are in phase, if the crests are meeting up with crests when they come out, then you're going to get constructive interference and you'll get a bright reflection. If, however, I have a crest meeting up with a trough, as I've kind of drawn it here, then what we're going to see is we're going to see no reflection because the outgoing rays of light will cancel out, and then all the light will instead go and transmit. So it's kind of interesting that the incoming ray of light has to know what's happening at that second surface, it seems, in order to know whether that ray of light should reflect or not. So that's just, it doesn't actually work this way, but this is the way we think of it. So it's almost as if that incoming ray of light knows the future. So we'll have constructive. If we have constructive interference, it's bright reflection. If it's destructive interference, it's no reflection. So again, we're interested in those two waves and what's going to happen. So if we look at the light going down through N2 and back, we're interested in that film thickness, and we're going to ignore that it's coming in at an angle. We're going to assume it's coming straight in and therefore down and back. We don't have to worry about a sine or cosine or anything like that. So in this course, we're only going to be interested in the film thickness itself. And you might think that the path length difference from the top of N2 down to the bottom of the thin film and then back to the top, that's going to be twice the thickness of the film, assuming I'm going straight up and down. And based upon what you might know from double slit interference or something like that, the path length difference should ring a bell. And if we write that that path length difference is, say, twice the thickness, and that path length difference is some number of wavelengths of the light, we might be inclined to think that, well, if it's a single wavelength, then that path length difference will be one wavelength, so it'd be half a wavelength down and half a wavelength back, and the waves would be back in phase if they were in phase to begin with. So the incoming light coming this way, this reflection, if this is half a wavelength and that's half a wavelength, then I will be exactly one wavelength off. And so with one wavelength, I would get constructive interference. The same thing as if I had it was two wavelengths. So this would be one wavelength down and one wavelength back up. So again, I'd get constructive interference. And then if it's three wavelengths, again, constructive interference. So if that number of wavelengths that's equal to twice the thickness is one, two, or three wavelengths, then I'm going to get constructive interference. And then if I'm off by half, then a half wavelength, just like before, will be destructive interference, 1.5, 2.5, because then the waves will be arriving out of phase. Now that seems like a pretty logical explanation. However, there's a problem with that. There's actually two problems with that. Let's talk about the first problem. The first problem has to do with how waves behave when they reflect. When a wave passes from one medium to a new medium, we know that part of the wave is transmitted and part of the wave is reflected. However, if it's going from, say, a lighter string to a heavier string, or in our case, from a smaller n to a higher n in terms of index of refraction, the reflected wave is out of phase, or we might say it's flipped. So instead of coming back on the same side, it's going to come back on the opposite side, which is going to throw us off by half a wavelength. So again, we're going to have a problem with the path length difference. If the wave flips, now we've got trouble where the wave's not going to be as it should. However, if it's going from heavy to light, if it's going from a big N to a smaller N, or a heavier rope to a lighter rope, then it's going to reflect back on the same side, so it's going to stay in phase. So we've got to worry about that reflection and whether that reflection is going to flip the wave pattern or not, because if it does, it throws off our constructive and destructive interference. Now, it is important to know that the transmitted wave is always in phase, so we never have to worry about that flipping or not. So now we know that at each reflection, the wave may flip. If this is going to be a flipped wave, what it would do is it would take all of these crests and troughs and turn them around and turn the troughs into crests and the crests into troughs. And so I would wind up with a wave that's opposite the initial wave. Same thing here. If this wave flips when it hits that boundary, then it's going to flip the wave right here so that I'm going to get troughs where I used to have crests, and then that wave will transmit and it will remain inverted. So I've got to worry about what's happening at both of those surfaces and whether I'm going to flip or not. So if N1 is less than N2, if it's going from light to heavy, then I'm going to have a flip of the wave on that surface. And then if N2 is less than N3, again, the reflected wave will flip and I'll have to worry about that boundary. So if we go back to what we had before with the path length difference and twice the thickness equal some m times lambda, well, we still have m equals 1, 2, 3. It would be constructive, but that's only if it doesn't flip at all or if it flips twice. So that's one situation where either it doesn't flip at all or it flips twice. So that would be, n2 greater than n1 and n3 greater than 2 to have no flips, or they're both or N1 is less than N2 and I get one flip, N2 is less than N3 and I get two flips. So two flips would also happen to be, this would work if it's no flips or two flips. But if I have one flip, if I have it only at one surface and not the other, then I'm going to reverse whether it's destructive or constructive with a half and 1, 2, 3 versus a half, 1.5, 2.5. So you'll notice that it flips between constructive and destructive. If I only have one flip, it's going to throw me right off. So where I would expect constructive, I'm going to wind up with destructive. So, confused yet? So let's move on to the next thing. Now we can say that that would be good, but we have another problem, and the problem is the lambda that we're talking about. Because we were talking about the thickness having something to do with the wavelength of light, but the lambda has to do with the incoming ray of light, not the ray of light wavelength when it's in the second substance. So it turns out that the wavelength will change when it enters a new substance. If we know that the index of refraction equals c, the constant speed of light, divided by the velocity in the substance, so that's the definition of index of refraction, so n is c over v. We also know that the velocity, that the speed of the light is going to equal the frequency times the wavelength. So these are two things that we should know before. But if we want to find out about the wavelength here and the wavelength here, we can combine these two equations also with the knowledge that when a wave travels from one medium to another, the frequency will always remain the same. The frequency depends upon the source of the disturbance, not the medium that it's traveling in. So the frequency remains the same. So if we have a constant frequency, then the frequency in the first substance is going to equal the frequency in the second substance. If we rearrange this equation, we can get that the frequency is going to be the speed divided by the wavelength. And so if the speed is the frequency divided by the wavelength, then we can replace the frequency with the speed over the wavelength. So I get v1 over lambda 1 equals v2 over lambda 2. Now we can take this second equation, and if n is c over v, then I know that v is going to be c divided by n. So now I can replace the velocities with the appropriate c divided by the n1 or n2. So what that gives me is c over n1, which we have replaced for v1, and c over n2 we've substituted for v2. And then since c is constant, we can see that we could cross out the c and make that a 1, and cross out that c and make that a 1. And so if 1 over n1 lambda 1 equals 1 over n2 lambda 2, we also know that n1 lambda 1 equals n2 lambda 2. This is not on your equation sheet, but it's one of those few things that you can either derive from scratch or maybe memorize this one. I don't encourage you to memorize much, but this is a good one to have when you're doing thin film interference. So now back to what we had before with the path length difference, and if one flip or two flips, and these conditions, now you'll see that I've changed that to lambda 2 because I need the wavelength in the second substance. So now we have something that's reasonably comprehensive, but it looks like it's reasonably challenging. So is that complicated enough for you? But now here is where I'm going to make it easy. This is something that I came up with and I'm pretty proud of, so I hope you'll enjoy it as well. And if any other physics teachers are watching, I want this to be part of the AP curriculum, so if you see it on the AP exam, you will grade it as correct and not take off any points, because this is a good one. All right, so what we're going to do is we're going to look at this wave as it comes in N1, transmits to N2, and reflects off of N1, N2 boundary, and then reflects off the N2 boundary and transmits back into N1. And so one question we're interested in, which is always going to be the question that we're looking for, is will it reflect? Will the light reflect? And we've determined that we'll have constructive interference under all those complicated conditions. But what we want to do is ignore those complicated conditions and let's get to something really simple. So the one question is, will it reflect? So we have two different situations. If the indices of refraction N1, N2, N3 are in order, either N1 is less than N2 and N2 is less than N3, or vice versa, what that means is we'll either get no flips or two flips. So if they're in order, it'll be no flips or two flips. If they're out of order, if say N2 is greater than N1 and greater than N3, then we're only going to get one flip. So either they're in order or out of order. Now, when we work out the math, you'll see that what's interesting is that the film thickness is interesting if it's either a quarter of the wavelength in the substance, so a quarter lambda 2, or half of the wavelength in the substance. If it's half the wavelength, then I have a chance for the path length back and forth to be doubled into a full wavelength. And if it's a quarter wavelength, then the path length down and back could be a half wavelength if I go down and back, so I'm doubling it. So that's why I'm interested in the thickness being some multiple of quarter or some multiple of a half. So those are the two interesting parts there. Now, if I draw a grid here, the way to remember whether it's going to reflect or not is I'm going to use the phrase in order, no quarter. You can remember that, in order, no quarter. If the indices of refraction are in order, as in this first case, in order here, if the indices of refraction are in order, then if the thickness is 1/4 wavelength, then it will not reflect. In order, no quarter. So if the thickness of the film is 1/4 of the wavelength in the substance and the indices of refraction are in order, then I will not get a reflection. It'll all transmit. And then if it is a half wavelength, then that would be, yes, it will reflect, because I would be off by that half wavelength again. Sorry, by a half wavelength when I double it by the film thickness. So if it's a quarter wavelength, it will not. If it's a half wavelength, it is. However, if I'm out of order and a quarter wavelength thickness, then it will reflect. And if I'm out of order and it's a half wavelength thickness, then it will not reflect. So in order, no quarter, you can quickly draw this little table and remember that if the indices are in order, then a quarter wavelength will not reflect. And so if you're looking for the minimum thickness that it will not reflect, then, and the indices are in order, then you just need 1/4 of lambda 2. And remember that n1 lambda 1 equals n2 lambda 2. So this is the way to solve those problems. In order, no quarter. It's going to be a lifesaver. I hope you enjoyed that, and I will see you again, hopefully face to face, after this whole pandemic thing is over. So enjoy your learning. Bye-bye.